We learned about first law, we learned about second law. Now we move to another law, which is the gravitational law, the law of attraction. Newton discovered this law, which is simply a universal law that says all objects attract each other. All objects attract each other. So if you have an object mass m1 here, another object mass m2 there will be a mutual attraction between them. And this force of attraction is directly proportional with the product of the masses and inversely proportional with the separation between their centers, r squared. Okay? The proportionality constant here is G. It is called the gravitational constant, the universal gravitational constant. For SI units, it is 6.67 by 10 to the minus 11 in Newton meter squared per kilogram squared. Okay? This is the universal law of gravity. Because of the law of gravitation, all objects near the Earth's surface are attracted to its center. And because of this attraction, we have our weights. As you know, weight is different from mass. Weight is equal to mass multiplied by G. G is the gravitational constant of Earth, 9.8 meter per second squared. Okay? So this is just because of the law of gravitation. One other way to write the same equation, when we apply the law of gravitation, the mass of the object, the mass of Earth, and the radius of Earth that separates the person or the object from the center of Earth. So we write the weight either as mg or as g, mass of Earth, multiplied by mass of object divided by r squared. So this is equal to that, mg equals gmem over r squared. We cancel m from both sides, and now we have this equation for G. G is equal to the universal gravitational constant multiplied by mass of Earth divided by the radius of Earth squared. If we substitute for G, 6.67 by 10 to the minus 11, and for the mass of Earth, 5.97 by 10 to the 24 kilogram, and the radius of Earth, 6.37 by 10 to the power 6 meter squared. Evaluate, this is 9.8 meter per second squared. So now we are educated. Now we know from where we have this 9.8 meter per second squared for the gravitational constant. Okay, this is how we calculate it, this is how we get it. Okay, so if you move to a mountain, R may increase. If you move up in a spaceship above Earth, R may change, and changing R will change G slightly. Okay, but as long as you are at Earth's surface at sea level, it is 9.8 meter per second squared. This is just an example. This is the weight for a 70 kilogram person on Earth. 70 by 9.8, it is 686 in Newton. If that person is in a balloon, the gravitational acceleration may change to 9.76. So the weight there will be 683 Newton. So if a scale is used to weigh that person at Earth, the ground, it will be 686. If the person weighed himself or herself inside the balloon, the reading would be different. And now we understand why it is different, because G is different. At 3 Earth radii from the center of Earth, the acceleration of gravity is 1/9 its surface value. True or false? Based on what we learned. Any suggestion? Ryan?
Is it true?
Yes. Thank you. Because we have the R square dependence. R squared, so the distance will be squared. If it's 3 R's, so now you have this new factor 1/9. Thanks. 1 kilogram of gold would have a greater value on Earth than on the moon. What would you say? Diego? Any suggestion?
Is it false? Maybe I'm thinking of it backwards.
Why you think it's false?
Well, because aren't things on the moon? So if you had, oh wait, because I was thinking if you had a kilogram of gold on the moon, then it would be more. Like if you brought that kilogram.
Okay, thank you for this nice discussion. Let me ask you this question. What is a kilogram? A kilogram is a unit of mass. It is a unit of mass, right?
Oh, okay.
So do you expect the mass to change between Earth and Moon? Mass will not change. Weight will change. Weight, which is mass by gravitational acceleration, yes, our weight on the Moon surface would be 1/6 of our weight on the ground. But our mass will remain the same. Mass is the amount of matter in our bodies, for example. It will remain the same. Okay? So back to this statement. Ina, I thought you want to say something. What do you think? Is it true or false?
False.
Okay. So the mass is independent, thank you. The mass is independent of the local acceleration. So 1 kilogram of gold contains the same amount of gold on Moon as well as in Earth. Thank you, and thanks to Emerson also.